right. So welcome back, everyone. This is the second meeting for this book club. Um, this week we're taking a look at nodal analysis and loop analysis. So this is chapter two of the book. So I've gone and kind of revised the schedule of things that we're going to be looking at. Um, I've got it here, and let me make sure I'm recording. Oh yeah, so that's good. So I haven't changed it here yet, but basically what I'm gonna do is I'm gonna push op amps to next week, and it kind of makes more sense, right? Because um, kind of awkward to cover both op amps and these circuit analysis techniques in one go. So hopefully we can keep on track with the rest of the material here. But it looks like we have another week where we're just covering one topic. So worst case, we just push another thing one week and hopefully everything will stay balanced here. Um, but so that's what we're going to be looking at this week. And let me publish this real quick. All right. So there's that. And we're going to kick things off just with a quick recap of last week because we didn't quite get to all the example problems. So here's just kind of a list of all of the learning goals that we set out to accomplish, I guess, learn last week, right? So there's reviewing the system of units, right? That was pretty straightforward, hopefully, for those of you that have taken physics. And we had mentioned that, as units appear, we'll actually go and define them formally, but we don't necessarily need to right at the start. The next learning goal was learning, knowing the definitions of voltage, current, and power. So these should mostly be review from the previous quarter, but voltage is kind of a difference in potential and voltage potential. Current is how much charge is moving, and then power is just the product of voltage and current there. And then we also looked at symbols for independent and dependent sources, right? So those kind of look like this, right? So that's a voltage source. This is a current source. And so these are independent sources, right? And then if you find those in a more diamond shape, these are dependent sources. So most of our examples are going to just be looking at independent sources. Um, Using dependent sources, they tend to come up more in the study of transistors where they're used to model different aspects of the transistors. Um, so we'll get into looking at dependent sources once we get to later chapters, or even if we look at electronics in the future together here. Um, Learning goal 1.1-4 is looking at power absorbed using passive sign convention, right? And that's just the idea where when I'm analyzing power in a circuit, I'm always considering the current to be going into the positive terminal, right? And so in this sense, it's absorbing power. And so if the current, right, actually ends up to be going into the positive, right, this higher potential as we had defined it to be, then power is positive and it's absorbing power. If after the analysis we find that the current is actually going the other way or the current's negative, then the power is less than zero and this element is supplying power. Then we looked at Ohm's law, right? That's just this relation where the voltage is proportional to the current with this constant of proportionality is just the resistance there. And then we looked at Kirchhoff's current law and Kirchhoff's voltage law. So these are, what goes in must come out, and what goes up must come down. So pretty simple there. And obviously for all these chapter two learning goals, we're going to go through and look at the examples to get a better idea of them. Um, so 2-3, we want to know how to analyze single loop and single node pair circuits. Um, and so we had talked about the concept of a loop, right, where it's just if I have some elements connected together, right, this circuit, for example, has two loops, right? There's a loop, and well, actually, this is also a loop, right? But the circuit has two, these are called meshes, and we'll actually get into that today. So this is not an example of a single loop circuit, right? If I had just removed that other branch, that would have been a single loop circuit, and then single node pair. So we also had talked about the idea of a node as just being that connection between all, right? For example, if I have a voltage source and maybe a resistor, right? So this is a single loop circuit. The junction, where el two or more elements meet together is a node, right? So this is a node. And so this, again, this is not an example of a single node pair circuit, right? Because there's a few nodes here. Single node pair circuit would be something like this, where I have these elements and there's a bottom node here, top node here, and so that's a single node pair. There's just one pair of nodes. This is a good example of a single loop circuit. And so part of the learning goals for chapter two was to be able to analyze these two types of circuits here. Um, and then we had talked briefly about Y delta transformations, kind of showed an example of the I think the delta to y transformation, but we didn't look at the equations for the y to delta transformation. Those are in the book. They don't come up that often though, so I don't think we'll look into any more detail there. Um, and then the last learning goal was just knowing how to analyze circuits containing dependent sources, which kind of just follows directly from all of the other learning goals. Um, so that's all for the learning goals. Um, And so at this point, right, I want to go through and do the example problems that we didn't get a chance to do. And in order to do so, I'm going to again go and share my iPad screen. All right, so let me make sure I don't have to do this again. All right, can you guys see the iPad screen? Yeah, I think so. That's should be good. Let me know if you can't though. Uh, That should be sharing. So for the first example problem, we're looking at 2.1, um, and we're interested in the current and power absorbed by the resistor in this figure. So we have a voltage source that's supplying 12 volts and a resistor that has a value of 2 kilo ohms. So we have a current here. Um, And so again, this is kind of an example of a single node pair circuit, but this is actually a pretty simple circuit. And we know that by Ohm's law, the current is given by the voltage divided by the resistance. And in this case, we know the voltage across that resistor or that resistance, right? This is going to be 12 volts. And then the resistance is 2 kilo ohms. So I'm going to write that 2K. And so this ends up being 6 milliamps, right? So whenever I have K in the denominator, that just brings up a M in the numerator, right? So K is 10 to the third, M is 10 to the minus 3, right? So if I have a K in the denominator, it's pretty trivial that that just becomes an M in the numerator there. Um, so that's the first example, pretty easy. Next up, 2.5. So we are looking at this network in figure 2.5. So we have a current source, a couple resistors, voltage source, another resistor, another voltage source, um, resistor there. So a bunch of stuff going on. It's getting starting to get moderately complex here, right? So we got R1, R2, R3, V1, V2, R4, R5. Um, so this is a pretty academic example of a circuit, right? This isn't really um, all that practical. At least I haven't seen anything like this, but maybe someone else has. Um, but all that we're trying to do here is write KCL for every node. And so in order to do so, right, we need to actually go and figure out how many nodes there are and what currents are going in and out of them. So they've labeled this top node, node 1, this one, node 2, this guy, node 3, node 4 here, and node 5 is this bottom one. And so this is just an example of writing KCL equations, really. Um, and in order to do something like this, we have to define which way the currents are going in the first place. So they've defined I2 going this way, I3 going this way, I5 here, I8 there, I7 here, and I4, I6, and then I1 is just that source right there. Um, and so I think one thing that comes up a lot is, well, how do you know which way the currents are going? And the answer to that is you don't. You don't know until you actually do the analysis. And after you do the analysis, if those currents end up being negative, then they're going the opposite direction and you were wrong. And you'll probably be wrong most of the time. And that's okay. So we're going to start off with node 1 here. So I've got I1 going in, and I've got I2 and I3 going out. And so that's equal to 0. And just as a reminder, KCL says that right, if you sum all of the currents into the node, it should be 0. So what goes in must come out, basically, right? Because if I say into the node, well, you can have these guys, these are kind of just like negative currents into the node, basically. Um, so if you add up all the currents at a node, that'll be 0. Um, all right, so moving on. So number 2. So at node 2, I've got I1 and I6 going out and I4 going in. I've got I4 minus I1 minus I6 equal to 0. And then if I go on to node 3, I've got I2 going in, I2 and I5 going in. and I4 going out, and so that's going to be 0. Um, and I could go on and do this for the rest of the rest of the nodes, but in the interest of time, I'm not going to do that. I'll let you guys do that. Hopefully you get the idea, right? So we just add up the currents going in, subtract the currents coming out, and that should go to 0 for all of the nodes. Um, are there any questions on that, I guess? Or are we good to move on here? Oops. Nope. All right. So next up, we're looking at 2.9. Um, and now, so this is starting to get a little more into the analysis, I think. So here we're looking at this kind of circuit. So we've got a voltage source, resistor, another voltage source, the resistor, voltage source, another resistor there. So we've got R1. This is 30 volts, 5 volts, R2, and so they've defined the voltages like so. All right, so that's the circuit we're looking at, and this time we're trying to find the voltage across R3. So find VR3. And in this case, we're looking at an example of KVL, right? And so in the previous example, we had looked at KCL, but this circuit we can use KVL, which as a reminder is if you sum the voltages in a loop, then that should go to 0, right? So what goes up must come down. Um, in this case, it looks like they're using the convention where they're traversing kind of, I want to say in this direction. And it looks like every time that they hit a positive sign while they're traversing, they're going to call that a positive voltage. So for example, if I start up here and I start traversing and I go through R1, I've hit this positive sign. So I have plus VR1. And then if I traverse from here to here, I've entered a negative sign, so I'm going to subtract 5, right? And I hit a positive sign here, so this is going to be plus VR2, negative sign there, so minus 15, hit a positive sign, so plus VR3, and then I finally close the loop and I hit a negative sign, so I'm subtracting 30. And so that should equal 0. Um, So this is pretty straightforward, right? To solve for VR3, I just take VR3 and I move everything else over. So I got 30 plus 15 plus 5 minus VR1. So this would require us to know what VR1 is. Oh, and sorry, I missed our VR2, so minus VR2. And so it looks like in this case, they define that to be um, 18 and 20, 18 and 12. So this is 18, this is 12. And so I can solve that. So this is 45, 50 minus 30. So VR3 is 20 volts. Um, so far, so good. I know that one can be a little weird. Um, but it's very, it's very simple, similar to the idea of KCL, right? What goes in must come out. So we add up the currents going in, we subtract the currents going out, in this case, we're going around in a loop, and whatever positive signs we hit, we're gonna add those up. Subtract the negative signs.
I got a question, RJ.
Yeah, what's up, Lucas?
Do you know if professors are like kind of particular about the sign convention on like if you go into a positive, that's a
Yeah,
positive
it
voltage?
really depends on who the professor is. I think I've known some to be particular on that,
Okay.
but it
But the
actually
math
it
the
doesn't
math is all the
matter.
same though,
Yeah,
right?
the math is all the
Yeah.
same, so it's really unfortunate that they would be picky about that because that's like
Okay.
objectively wrong. But yeah,
Yeah. All right,
yeah,
thanks.
yeah, sure thing. So yeah, that's just one thing to keep in mind when you're taking the class for real. Gotta follow whatever convention they use because sometimes that can be make or break for your grade for some reason. All right. So 2.13. Um yeah, because like on that note, I actually use the other convention. I actually when I'm traversing, whenever I exit, I look at whatever I'm exiting. And so that way, when I'm looking at like a voltage source, right, and I know the current's always going this way, I'm always exiting a positive side. So I don't know, it's kind of weird that the book would use this other convention. Um, all right, so for this guy, we're looking at voltage source, and we've got like a variable resistance up top and a fixed resistance here. Um, and we're interested in this voltage V2. And so we got a source voltage here. Um, and I don't really want to work this question out too much. They're kind of just looking at the power. Um, what when you change the resistance. Um, so they're changing R1 basically from 90 kiloohms to 15 kiloohms, and they're interested in the power absorbed. Oops. And so they actually just jump to the definition of the voltage divider. So we kind of had looked at that last quarter, but the general idea is if I am giving, some kind of voltage source into a network of these two resistors like this, then the source voltage is going to get divided down, right? As seen by this, call this kind of like the output voltage of the voltage divider. Um, and so it's going to be scaled based on this resistance, right? Because V is equal to I times R. So V2 will be proportional to R2, certainly. And it will also depend on the equivalent resistance of this network. And so this is actually two resistors connected in series. So we just add them up like that. And so that will give you, a closed form kind of equation for what that output voltage is, that V2 there. Um, and so with that, you can play with this R1 since it's a variable resistor and see how it impacts the power. And so that would just be good for you to maybe do on your own, right? So P is V times I. And so we know by Ohm's law that I is V over R. By Ohm's law. So P is also V squared over R. Um, and so since we kind of have that equation for the voltage, we can kind of solve for the power and see how it impacts the power by changing that top resistance there. Um, but yeah, so since we're kind of pressed for time here, I didn't think I might have picked out too many example problems here. I'm gonna try to stop the example problems at 9:40 just so that we have time to at least 10 minutes to cover the chapter. So let me try to condense the list that I've got here into to more reasonable things to go over. Um, 2.23. All right, so 2.17 is probably a good example because it's kind of the first occurrence of this multiple loop circuit. So we have a current source, which is supplying zero point 0.9 milliamps. Got a resistor here, 60 kilo ohms. Another resistor here, 40 kilo ohms. And another resistor here of 80 kilo ohms. And they've defined this to be the output voltage. And this be some voltage V1 there. And so it looks like we want to find I1, I2, and the output voltage VO. And so going back to the figure that they had, I1 is the current that's going through the 60 kilo ohm resistance, and then I2 is the current going into the 40 kilo ohm resistor there, resistance. Um, and so here they're applying the concept of current division. And so current division has a very similar form to voltage division, right? Um, but instead of more voltage um, being seen across the higher resistance, we have more current being seen in the lower resistance path, right? The path of least resistance. And so here we take I1, right, to be 40K plus 80K divided by the sum of all of these. Oops. Um, and it looks like they don't really give the form, like the general form of the voltage or the current divider there, which is kind of annoying. But it's kind of like it's almost like the opposite of the voltage divider, right? For the voltage divider, we usually have two resistances in series like that and a voltage source, right? And so this is called the output voltage. And again, this output voltage is just, oops, proportional to that resistance that we're looking across. But for the current divider, we're actually looking at two resistances in parallel, right? They're between the same two nodes here. And instead of, voltage being the output thing that we're looking at, we're actually looking at current. Um, and so it kind of depends on which path you want to look at. But let's just call this the output current across R2. And this output current is going to depend on the input current, right? So whatever the source current is, and instead of this resistance, it's kind of interesting. We're looking at the other path resistance. So in this case, it's R1. And again, we're looking at the sum of the two. Um, so anyways, so I1 in this case, right, is just going to be that times the source current, which in our case is zero point 0.9 milliamps. And so that turns out to be zero point 0.6 milliamps. And you can follow the same process for I2, right? Just take the other path here. So that's 60K divided by this guy here, just the sum of all of them. And I'm running out of space, of course. And so this ends up being zero point 0.3 milliamps. All right. So, oh wow, it's already 9:41. Great. So yeah, unfortunately, we're kind of running low on time here. I think I might have been too ambitious with our schedule, but um, you ought to read through the other example problems on your own time, if you have time. But I think that'll probably do, right? Because that's kind of just getting like an introduction to these kind of ideas of really the important takeaways are Kirchhoff's current law, which we examined here, right? Where we're just adding up the currents going into and out of a node, and then Kirchhoff's voltage law, which, we're going around a loop. We're adding up the current or the voltage rises, subtracting out the voltage drops, and then summing that to zero. Um, Everything else that follows in chapter two is kind of just um, a special case of these two laws here. And we'll look at the laws again over and over again uh, for most of the rest of circuit theory anyway. So if you're lost now, I'm sure you'll pick it up later. But if there aren't any questions, we'll move on to chapter three here. Um, and it looks like there are none. So let's go ahead and jump right in. Okie doke. So hopefully I'm sharing my screen here. Let me know if you guys don't see it. You guys should be seeing the slideshow now. Um, so again, this week we're looking at nodal analysis and loop analysis. So these are two of the probably some of the most important techniques that you can take away from this class, especially nodal analysis. That pretty much works everywhere, wherever you want to do analysis. So here are the learning goals. 3-1, calculating currents and voltages in circuits with multiple nodes and multiple loops. I mean, so we kind of covered that, in those other two examples, but we're gonna formally define um, these multiple node and multiple loop circuits, I guess, and kind of look at an easier way to analyze them because it can take a lot of effort if you don't have these formal algorithms in place. And then we're going to be employing KCL to perform nodal analysis. And so this is used to determine all the node voltages. And whenever you have resistive circuits, you've pretty much completely solved the circuits once you've figured out either the voltages or the currents. And, we're either going to do nodal analysis to find the voltages, or we're going to do what's called loop analysis to determine all the loop currents. Um, and then the last learning goal is just determining which of the two analysis techniques should be utilized. Um, and so I didn't actually put anything in the slides about that, but it pretty much just boils down to which technique leads to less equations to have to solve. And so that can be kind of tricky to determine at a first glance, especially when you're kind of new to this stuff. So I think it's more suitable for when you revisit the courses when you'll really need to figure out which of the two techniques you'll need to use. Um, so just jumping right into it, to solve these complex circuits, we need an algorithm, right? We need a set of steps to really go through and solve the circuit. It's going to be a lot faster than poking around trying to figure out all the voltages and currents. And so again, you got nodal analysis. You'll also see this referred to as node voltage method. So that's what I learned it as in the textbook that we used at Cal Poly. So the same thing. And then there's also what this book calls loop analysis. And so you'll see that called mesh current analysis in some places. Um, So personally speaking, I'd say node voltage is probably the my go-to analysis technique if I ever have to analyze a circuit, but that's just me. So all right, so getting into nodal analysis. So the first thing that we need to do is select a reference node. And so again, this is just we call it ground, right? Because this is where we consider to be the zero potential for the purpose of analysis, usually. Um, That's obviously not always true, right? There's not really a great zero potential in every single circuit that you encounter. Oftentimes, if you have a connection to like the physical earth ground, then that's, kind of considered a good zero potential. But this isn't just something that, exists in nature, right? This is zero potential. But for the purposes of analysis, right, we call it the reference node. And it's just we usually choose it to be the node that has the most attached branches. So in this case, I've got this bottom node here. And so a branch is just, a step from one node to another. And in this case, I've got a branch through V1, I've got a branch through R4, I've got a branch through R5, branch through R6, right? So this bottom node has four branches that are attached, so it's probably a good choice for the zero, for a reference. Um, right, and so that's always the first step in nodal analysis. So once we've selected the reference node, then we go and write a constraint equation for each voltage source. So in this case, we've called this bottom node the reference still, and we're kind of given this voltage up here for free, right? This node voltage. So this is just going to end up being whatever the voltage of the source is. And so for, the purpose of a numerical example, I've just called this 6 volts, this V1. And so that would be an example of a constraint equation. And so you'd go and do that for every single um, voltage source that you have for nodal analysis here. And so once we've gotten all of our constraints out of the way, we go and identify all of the unknown voltage, all of the unknown node voltages. And so I don't think I had mentioned this before, but node voltages are all with respect to our reference. And I know we looked in the past at voltages across resistors, right? So this R1, for example, the voltage drop across it would be the difference of this node voltage and this node voltage, right? And whatever current and whatever direction the current's going. Um, but that's just one thing to keep in mind, right? These node voltages aren't voltages in the sense that they're appearing across um, elements. They're all with respect to the ground, right, or reference node here. Um, and so in our circuit that we've got, that I've drawn here, we know that um, node 5 is 0 volts because that's our reference, right? We've defined it to be 0 volts. We know that node 1 has a voltage of 6 volts because there's a path from 5 to 1. We're going up through this voltage source. And that leaves us with 2, 3, and 4, right? Node 2, 3, and 4 are all unknown node voltages. We don't know, we don't really have an equation for them quite yet. And so that's kind of like the important next step, right? So we select the reference node, write all of these constraint equations for the voltage sources, and then we identify all the unknown nodes, and then we write KCL equations at each of these nodes. And so you'll recall that K by KCL, what goes in must come out. And so in order to do this, we actually have to go and define the current directions. So I like to define them such that it's always falling away from the source and dropping to ground. So that's just my convention. Obviously might have, it doesn't really matter how you define them usually, but that's how I do it. So in this case, I1, right? You can imagine current pumping out of this voltage source and it's going through R1 because it has nowhere else to go. And then it's falling to ground through R4. It's also trickling down to ground through R2, through R5, and then through R3, through R6. They're all going down to ground. Um, and so if we write KCL equations based on these current directions that I've defined, just looking at node 2 first, we have I1 minus I2 minus I4 is equal to 0 because I have I1 going in, I2 and I4 are both going out. And then moving on to node 3, I2 going in, I3 and I5 going out. So I2 minus I3 minus I5 is 0. And then lastly at node 4, we have I3 going in, I6 going out. So I3 minus I6 is 0. Um, pretty straightforward, hopefully. So once we've written all the KCL equations, we need to go back and write them in terms of voltages, right? Because the goal of using this nodal analysis technique at the end of the day is to find all of the node voltages. So we're going to go back and we're going to take our KCL equations and we're going to write them in terms of the voltages based on the directions of the currents. And so in order to do this, we need to remember that current is going from high to low potential, right, by convention. And so, for example, this I1, we're going from node 1 to node 2. So that's high to low. So V1 minus V2. And I've actually gone and written the resistances in terms of conductance. So you'll remember that inductance is represented by G, and so this is 1 divided by R, just the reciprocal of resistance. And there isn't really any practical need to do this other than it makes the analysis a little bit easier. Um, right? Instead of having to write a division sign every time I have a 1 over R, I can just write the product. So I've gone and done that. So you can imagine this I1, just for example, is V1 minus V2 divided by R1. And so what I've done is I've replaced that R1 with the G1. So I just have V1 minus V2 times G1. And so I've done that kind of for all these other instances as well. And so that just makes the analysis a little bit easier. At least it's a little bit cleaner, right? At the very least. Um, so here I've gone and done that for all of the other KCL equations that we have, right? I'm not going to go through each example, but maybe I'll go through the second one again. So I2, right? If I look at I2, it's going from node 2 to node 3. So that's V2 minus V3. And I'm going through R2. So I'm just going to multiply this by the conductance G2. And then I'm subtracting out I3. Um, so I3 is going from node 3 to node 4. That's V3 minus V4. And it's going through R3. So I multiply by the conductance G3. And then lastly, I'm looking at um, I5. So I5 is going out. So I5 is going from node 3 to node 5. And so here, this is kind of interesting. Um, we know that node 5 is 0, right? This is our zero potential. So I actually omitted that subtraction of V5 because I know that's 0. So I'm subtracting V3 times that conductance, R5. Um, yeah. So this is where, it gets kind of tricky. Because we've got three equations, three unknowns, and not everyone is all that well versed in matrix algebra quite yet. But I'm just going to show you guys how to do that in MATLAB because I'm not going to go through the process of solving all this by hand. Um, so the first thing that we want to do is group things in terms of the unknowns. And in this case, the unknowns are the voltages, right? We know what V1 is. That was given. That's the voltage of the voltage source. So I'll move that over to the side, right, on the other side of the equation. Um, but I'll start off with V2, right? And I'll look at all of my terms here, and I'll see that I have a minus G1 here, and I've got a positive, or sorry, a minus G2 there, and I've got a minus G4. Um, maybe I wrote this out wrong because I don't think, oh yeah, it is minus G2, sorry. So from this first KCL equation that I expanded out, my V2 contributions are minus G1, minus G2, and minus G4. And then V3 gets a positive G2, right? I've got a minus times a minus. So that's a positive G2. And so that's my first equation. And then from my second KCL equation, I just repeat the process, right? So I pick out all of the V2 terms, I pick out all of the V3 terms, and I pick out all of the V4 terms, sum those to 0, and do the same thing for the last equation here. And then I've written it out in this matrix form because it makes life easier. Um, right, so the way that this works is my first equation appears up here, right? So I got this first term, minus G1, minus G2, minus the G4. And I'm taking this guy, for those of you that aren't familiar with matrices, and I'm multiplying it by this guy. I'm taking my G2 and I'm multiplying it by V3, and I'm taking my 0 and I'm multiplying it by V4. And so all of this, right, if I add these guys up, I should get my first entry in this column vector out here on the other side. And you kind of just repeat that for each of these terms here, right? So for example, G2 times V2, right? I get this term, and so on and so forth. I'm not going to draw that all out. But anyways, so with that, we can use a little bit of matrix theory, right? So assuming that this matrix, which we'll call A, is invertible, um, and we'll call this guy X and this guy B. So what we have here is A times X is equal to B, where A and B are matrices. X is a column vector. Well, I guess B is also a matrix or a column vector technically, but we can use matrix theory to show that A inverse times B will give you X, right? You can solve. And it's kind of the same idea of solving a system of equations, really. Um, anyways, moving on. Um, so now we can actually go and solve this in MATLAB pretty easily. Once we actually have all the resistances, right? So I've got conductances here, but at the end of the day, that's just a resistance, the inverse of a resistance. So here, right, so I've got my resistances are just very arbitrary. 1K for R1, 2K for R2, and so on all the way up to R6. So I've done that in MATLAB here, right? I've defined a just kind of like a vector of resistances. So 1, 2, 3, 4, 5, 6, multiplied each of them by 1,000, right? Because these are all in kilo ohms. And then I've defined a conductance vector, I guess you could call it, to be just the reciprocal of all my resistances. And then I've gone and defined my A matrix, which again is this guy. Um, you'll see in MATLAB, we can separate um, each column term with a comma, right? So in the first column, I've got minus G1, minus G2, minus G4. In the second column, I've got G2. In the third column, I've got 0. And then we can move on to the next row with a semicolon, right? So I moved on to the next row here. Um, and so I've defined my A matrix that way. I've defined V1 as I had done before to be 6 volts. And then I've defined the B little column vector that we had here, um, just as it was. And then again, we can use matrix theory to figure out what the solution vector is. And that gives us 4.16, 2.56, 1.7. And so again, these are the node voltages V2, V3, and V4, right? This is our solution vector to our little matrix system here. Um, and so that's all great, but then we need to go out and actually verify that this is correct. So um, I went and simulated this in LT Spice, right? I've got my 1K, 2K, 3K, 4K, 5K, and 6K, and I've numbered all the nodes as we had done. And I've used the 6 volt source, and I did this dot op um, spice directive. Um, and again, we get those exact same node voltages just as calculated, which is always a good sign because it's it's a way to show that you actually are doing your analysis correct. So anyways, this is just a summary of the nodal analysis algorithm, right? So we choose a reference node. We write the constraint equations for each of the voltage sources. We define the current directions and write KCL equations, and we solve the KCL equations to determine all of the node voltages. Um, so yeah, great analysis technique. It always works, and I'd prefer it. So obviously we don't have time for this, but I honestly that this example that we just walked through here does a really good job of explaining it, and so I think you should pretty easily be able to follow the two examples in the book, and then as well as whatever example exercise problems that they've got there. So, um, with this remaining 7 minutes, unless there are any questions, I'm going to try to zip through loop analysis, which is pretty similar. Any questions? No? All right. All right. So loop analysis is very similar to nodal analysis, but it only works for what's called a planar circuit. And so these planar circuits can be drawn such that no conductors are overlapping. So for example, this circuit on the left is planar. This circuit on the right is not planar because I've got this kind of awkward connection here, right? There's no great way of drawing that. Actually, I don't know. I couldn't find a good basic example of a non-planar circuit, but anyways, um, basically, if you come across a circuit where it really physically can't be drawn, such that no conductors are overlapping, then that's non-planar. Um, so the first thing that we do in loop analysis is identify what's called a mesh, right? All of the meshes. And so these meshes are loops that don't have loops within it. So for example, here's a mesh, right? Mesh one, I've labeled it. Mesh two is here. And this outer loop is not a mesh because it has another loop, right? It has loop one within it. So that's not a mesh. Um, so once we've found all the meshes, we write these constraint equations for the current sources, right? So it's a little bit different than the nodal analysis. Um, and so in this example, our mesh current, right? Mesh one current is actually just the current of the voltage source because I1 is traversing like this. And so it's going in the exact same direction as I1, and I1 has nothing else flowing, no other elements really, going through it. So our mesh current is I1. Um, and so this would be, I1 is equal to capital I1. It's kind of awful convention there, but that is our constraint equation for this example, really. Um, And so once we've got all the constraints, we then write KVL equations for each unknown mesh. So for example, I2 here is our only unknown mesh. So we write our KVL equation. And so here I use the convention that I'm used to, where I'm coming out of the positive end of V3. So I called that V3, going down V2, going down V4. And so that should sum to zero. And then all we need to do is expand these KVL equations in terms of the mesh currents, right? So this is very familiar, to the node voltage method or the nodal analysis method where we write the KCL equations, but then we expand them out in terms of the voltages because the voltages is what we're looking for in that method. In this method, we're trying to figure out the currents, so we expand the KVL equations in terms of the currents. Um, so there we've got it there. My V3 minus V2 minus V4 turns into R3 times I2 minus I1. So this is kind of an interesting thing, right? So, sorry, I1 minus I2. I've got the current going, right? So I1 is going into the positive end of R3, right? The higher potential. So that's technically in the forward direction, right? So this is positive because by the passive current convention, or sorry, the passive sign convention, this guy wants to, dissipate power. So that's going to be positive. So I1 minus I2. So it's minus I2 because I2 is also flowing through R3, but it's going in the opposite direction, right? So I'm subtracting out I2. Um, In the case of R2, I only have the one mesh current going through it, right? And so that's going to be I2. So I've got R2 times I2. And then R4, we've only got I2 going through it. And just like in the previous example, we want to separate out all of our unknowns. So I'm pulling out I2. I'm looking at the contributions of this from this equation to I2. And so I've got a minus R3 here. I've got my minus R2 there, and then I've got minus R4 here. And so this is a much simpler equation to solve, right? I just take this because we know what the mesh current is. We typically know what all the resistances are, so I can pretty easily solve this just by dividing by this term, right? I can figure out what that I2 is pretty easily. And the next slide here, we've gone and done that. Um, Divide through, pick out just some arbitrary values in this case. Again, so just 1 kilo ohm for everything, 1 amp of current. Um, Plop that into MATLAB. Find that I2, this mesh current, should be minus 0.33 amps, which if you remember, we had defined I2 in this direction. And so if it's minus, then it's actually going in the other direction. Right? And so that's 0.33 amps that way. And and I, plopped it into LT-Spice just to verify all of my analysis, and it all worked out, and everyone's happy. Um, and so I think apart from the summary of that, right? So just a summary of loop analysis. So we assigned the loop current to each independent loop. I'm going to rewrite that to each mesh because we had defined mesh. We write the constraint equation for each current source, and then we write the KVL equations for each unknown loop current. And again, I'm going to write mesh current. Sorry about that. And then we solve the KVL system of equations to determine all of the mesh currents. So I know it's a lot to take in, especially at like 8 p.m., but hopefully you guys followed all that. Um, I think I'll stop the recording here, and I'm happy to take any questions on anything.